So now we have Pankaj. Welcome.
Pankaj.
Thanks. So Pankaj is a research scientist from the Machine Intelligence Group at Siemens. And I understand you've worked on quite a few shared tasks. Maybe you could just tell us a little bit which one was the most fun to work on.
Yeah. Okay. So, about the shared task, two of my PhD students started actually. I was not the initiator of those shared tasks. I finished my PhD and two students started with me, and they want to work on entity and relation extraction and understanding topic modeling that I'll talk today. And they wanted to understand the fundamentals of topic modeling and how to use them, especially in applications. So we thought, let's start with some shared task and let's understand entity extraction and relation extraction for them. That's how we started.
Fair enough, and we're going to hear a bit more about it, I think, as well.
Today, yeah.
Awesome. So, welcome to Pankaj.
Yeah, thanks a lot. Okay, so I'm Pankaj. I come from Munich. I travel today. I'm a research scientist at Siemens. I'm leading the AI NLP group there. I'm also teaching. I like teaching. I'm teaching deep learning for AI, especially recurrent neural networks and representation learning at LMU. Okay, next slide. He has already introduced, but the motivation is I recently graduated. I did my PhD with Professor Henrik Schütze at LMU. I love Zurich because I worked here during 2016 at IBM Research. I was a research intern. I could see some faces from IBM. That's what I love Zurich. But yeah, let's go to the next slide. Okay, so there's a lot to talk about, but we have only 20 minutes. So what I do is I'll focus much on the fundamentals. You see, I recently graduated, so I will mostly focus on some of the scientific aspects. So I talk about topic modeling. What is topic modeling? Many people get confused. What is topic modeling? And you see the title, Learning Beyond Sentence Boundaries. So the idea is learning representations beyond sentence boundaries. Okay. I talk about several contributions that I had during the course of my PhD and current recent works. I talk about relation extraction, what you can talked about, but I'll go beyond sentence boundary, how to extract relation beyond sentence boundary. And lastly, I focus on some of the applications and let's say shared task, some of the applications at Siemens that are running into the product, some of the research that are actually running in the product. Okay, so this is about topic modeling with transfer learning. Okay, so when you learn representation, especially in text, whatever you learn everything from the context. And what does it mean by context? Context is something that a neighborhood to you, okay, or a neighboring environment to you. For example, there is a word called food. A representation of food could be encoded in different forms, in different brains. For example, first brain might have a different encoding or different representation of the food called representation for food because it has seen a different environment, it has seen a different context. Similarly, for the second brain, it has a different encoding. Similarly, in the third brain, you have a different encoding because you have seen a different context. So context is the thing that I'm going to talk about today. Let's start. What does the context mean? Context means how far you can look at, or how far you can look at in the document, or you can look into the sentence. So semantics you define based on the context. So semantics could be local or it could be global. Local in the sense you learn representation based on n-grams. So you have a particular word and you learn representation looking at neighboring words which are within a sentence or constrained by an n-grams. However, you can have a global context, for example, topic modeling less. Global context in the sense that you learn word co-occurrences or word relationship looking at the context at a document level, okay? That's what I refer to global context. I mean, across sentences. Let's see some examples, So there is a word called Hawa, H-A-W-A. Can someone guess the meaning of the word Hawa? H-A-W-A. It could be of any language.
Indians allowed to guess?
Yeah. Why not?
Air.
Yeah. What? Air. Okay. Okay. Let's see now. Can anyone guess what is the meaning of HAWA now? Yeah. Food. Yeah. Food. Why? Because you see the context around it. Hungry and eat. Okay. How about this sentence? I put a cup of sugar in cooking Hawa. Now, is it still food? But yeah, sweet, dessert. Okay. Why do you say that? Reason because you look at the context around the target word. So you learn a representation for a word called Hawa, looking at the context. So actually the word was Halwa, halwa, which is typo, and still you can handle the typos looking at the context around it, which is sweet. Going beyond, one could have slot fillers. For example, you could have any word that fills this particular filler. Let's say this question one. This could be halwa, which is I just referred. It could be tiramisu, it could be cake, it could be pudding. Okay. What is the common property in all the occurrences of these words? One is cooking and one is sugar. So they have a common attribute called cooking and sugar, which all these four items possess so that you can cluster them. This is how representation learning works. Why? Because you share common properties, common attributes, you learn via co-occurrences. Okay? That's how you see word embeddings, synonyms, you see antonyms, that's how you see representation learning. Okay, few more examples. How about a word called chip? Okay, it could be a semiconductor chip, it could be potato chip, or it could be poker chip. All these are nouns syntactically. How about verbs? It could be chipping the soccer ball, it could be chipping the golf ball, or it could be chipping the ice. But if I say an n-gram, eating chip, one could easily guess, yeah, what does it mean? But how about this? Can anyone guess the meaning of chip belongs to or related to unhealthy? No, unless you are given certain context beyond the sentence boundary or at the document level. For example, you see a word called potato, bad, acrylamide, oily, unhealthy, high or fat. By the way, I am not a cheap eater. So you see the context and you see one could have a topic which is unhealthy just because you see a context beyond the sentence or beyond the n-grams. Similarly, you see electronic chip. It is difficult to say whether chip belongs to trading unless you see set of keywords like share, market, index, dollar, billion, false. Okay? So that's what the motivation of having this talk. So words in language, let's say, have local, I would say n-gram, and global, in the sense like they have document level, semantic, or contextual properties. Okay? Someone in the room might claim we can have complete sentence. Sania is serving a tennis ball. Who says first, who says second? Let's say who says first. Okay, maybe majority. Unless you see this word, you see this document. So you see that the chef has prepared tennis-themed dessert, including sorbet, white chocolate. It's a document. And then you see warm raspberry sauce drizzled over it. So semantics change. Even you have a complete sentence, semantics is defined by, if you have a document, mostly semantics is defined by a context across the document, beyond sentence boundary. Okay? Similarly, if you have different context for the same sentence, the semantics change. In this case, you have tennis championship, tournament, sports, that change the semantics of the whole sentence. Okay? So, language is contextualized. The core message, language is contextualized by n-grams, sentence, paragraphs, or document. How many agree? How many of you agree? Okay, so you got the message. Okay. Okay. No question. So we talk about document topic modeling. Document topic modeling in the sense like we learn representation at document level now. Okay. See, topic modeling in theory you say that it's a generative topic model where you learn word co-occurrences at document level. Fair enough. And the output of topic modeling, you extract some topics and you generate a topic vector. Topic in the sense you explain some explanatory vector or explanatory set of keywords. Essentially, if you read a literature or let's say Wikipedia page, topic modeling is defined as a document is a mixture of topics and each topic is a list of words. Let's look at it. Let's say we have a document, a chip is in an integrated circuit, whatever, I'm not going to read out because of time. There are 3 topics we assume. A topic model learns association between latent topic, which is this one, this vector. It has 3 topics, latent topic, and the topic modeling learns association of each latent topic with set of keywords. So here, first topic learns association with chip, circuit, electronics, transistor, semiconductor, for example, and learn another topic, association, about sales dollar billion market share, in the sense that topic modeling extracts a topic proportion vector, which has a semantics that document 1 has topic number 1 dominating as compared to topic number 3. Agree? Another document could have another set of topics. Here you see that topic number 2 is more dominating, in the sense that the two documents, document 1, let's say, and document 2 are actually similar just by topic number 3. So this is how you compare documents. This is how you compute information retrieval at document level. And the output is topic. That is what the beauty of topic modeling. You can see, you can visualize, or you can interpret topics. Here you see the first latent vector, in this latent vector first unit represent a topic about semiconductor electronic circuit chip, while the second about operating system, and the third is about share, marketing, trading, sales dollar. So this is what the beauty of having topic modeling. And it is completely unsupervised. And in terms of application, you can have information retrieval, you can have document similarity, one could use it for word sense disambiguation, and we can use the tool to analyze documents, large collection of documents. But what did I do during my PhD? This is what I did. So I addressed certain challenges in neural topic modeling. NTM belongs to neural topic modeling, where I saw neural topic modeling has a problem or has some limitation in data sparsity. Data sparsity means you have limited data setting, let's say. And then let's say, this is the first scientific direction I'm going towards. So we introduced word embedding aware neural topic modeling. This was the work in AAA this year. And due to this lack of context means you can have a short document, you can have a small document corpus. Short document in the sense, let's say a short text, for example, headline or tweet, it's very few words only. That leads to certain problems like certain challenges, like it is difficult to learn good representation, and it is difficult to extract topics, good topics, coherent topics, which is the essence of topic modeling. Here you see first topic, it has about wall in China in explaining a topic called trading. While the second topic says shares, price, profit, rises, earnings, the second topic looks more coherent. So the idea is how can we improve topic 1 such that it becomes topic number 2. Idea is very simple. You look at topic proportion. If you introduce, generally topic models have bag of word assumption. So if you take the two symbols, market and stocks, you see a similarity of 0%. But if you introduce, but you use pretend word embeddings, for example, a vector of market and a dense vector of stocks, you see a similarity of 0.7. So why not introduce such kind of a prior information, which is called transfer learning, into topic modeling? Okay. So this is what it did. So you see a word called market, you see a word called, sorry, because of animation, stocks here, and the similarity is 47. That's how topic number 3 is boosted in document number 1, in a way that document number 1 and document number 2 become similar. That the proportion of document 1, topic proportion of document number 1 and topic proportion of topic number 2 become similar just because of the topic 3. Okay. I will skip that. We analyzed our proposed model on 15 data sets using several measures like perplexity, negative log likelihood, topic coherence, what is the quality of topics, and document retrieval and text classification, and you see the scores. The code is also available. Now we saw that we have complementary representation, as you see in the motivation. You could have word embedding matrix, you could have word embedding representation, you could have topic embedding representation. So the idea is why not to introduce topic embeddings also in learning topics, and also to introduce from several sources. That's a paper on arXiv these days. So the idea is you have, let's say, representation of chips, microprocessor, chipset, microchip, chipset, chipmaker. This is a word embedding representation of chip, and this is a topic representation of chip. You see they are complementary to each other. Why? Because one encodes local semantics and another encodes global semantics. I mean the second one. And the idea is how can we introduce from several sources. One source of information in transfer learning could have a representation of chips, microprocessor, chipset, and another could have chocolate, chicken, potato, which is very different to the expectation of this document. So here, the idea is to find the relevant source of information, which is this one, and introduce into this model. Okay, so this was the model those guys are interested in. What it did actually in the end. So we found that minus GVT in the sense like you do not perform transfer learning. So without transfer learning, let's say this is a topic about natural calamity, where you say the strike and Jackson could be noisy words. Idea of global transfer is that it imitates some of the topics from your knowledge base. For example, topic word explosion and radiation are imitated by this topic, and the topic becomes more coherent or more explaining. Okay. How much time I have? Okay. 5 minutes. Okay. Okay. So lastly, I mean, we go towards compositional model. It's one of the favorite models these days, and it's very popular. And I'm still working on this, the second part, where we found that the topic model usually do not model the order of words. For example, market falls into beer territory and beer falls into market territory. Both sentences have the same n-gram statistics. So when you model into a symbol, both sentences have the same semantics, same representation, but they have different semantics. Like one is trading, another is non-trading. Another motivation of introducing language structure like chip could be a verb, syntactic structure, a chip could be a noun, a second syntactic structure. So whether this syntactic structure like word ordering and part of speech tags could help in topic modeling or not. So we introduced those into in our topic model, and it is known as text-to-vec, where we introduce LSTM-based language model into a topic model in order to improve topics. Okay, and if you see the topic here, it is about expression: nodded, shout, looked, smiled, stared. In the sense that all the topic words are coherent, but they have a syntactic property which is past participle. So you see the topic words are also coherent in terms of linguistic structure. So that was a contribution. You might also see topic-aware language model in the sense that now you use language model to improve topic model, but how about using topic model to improve language model? So the idea is very simple. We talk about the word chip. If you see the semantics within a sentence, it's difficult to resolve the representation. But if you have a vector, topical vector, which says that at the document level, the document is about circuit, electronics, computers, then one could learn better representation of chip. So that is very simple. You learn topic from topic model and introduce in language understanding. So one can resolve that the word is about chip. Okay. Okay. I think I'm running out of time. So maybe I'll share the slides, but I would like to skip this part. This was about topic modeling, but you also need representation learning beyond sentence boundary in relation extraction. Instead of extracting relation within sentence boundary. So the idea was very simple. You have entities, you have relation within sentence, but the idea is to go beyond sentence boundary. So here you see the first entity, Van Raben, the first entity, first sentence, second entity, polynomial group is in the second sentence. So the idea is how to extract relationship between the two entities across the sentence. We have a challenge there. There are a lot of noisy text. For example, you see here the red color. This text is not responsible or it's not relevant for extracting relation or detecting relation. So how can we have good representation, which is beyond the sentence boundary? So the idea is very simple. As Yakam said, we have dependency pass trees for the first sentence, dependency pass tree for the second sentence, and we connect them. In order to make a connection, and you run a bidirectional, like you have the subtrees, and then what you do is like you simply run a bidirectional RNN on the subtree. Can you see that? You run a bidirectional RNN on the shortest dependency path, and you run a recursive neural network on the subtrees in order to learn a representation for the trees. Very simple. So you run a combination of RNN, you run a combination of recursive neural network. It offers the best score. This was the shared task, I think, 2019, and it has a gain of 5.2%. In terms of application, we won the first, we won the information retrieval shared task, 2 shared tasks. This was about you have a query and you have an abstract. The idea is to rank the abstract based on the relevance of, based on the query document relevance. And the second task was fine-grained in sense, in an abstract, which sentence is actually relevant. And in the second one, we did information extraction, we did nested entity extraction, and then we also did relation extraction, along with normalization, entity normalization. I won't go into details, I mean, you can check out that. At Siemens, what we do? So we talk a lot about research, but how we apply. In Siemens, we receive a lot of tenders. Tenders like tenders about building trains, railways. So we have set of requirements. They look like that. It's a tender. Generally, tender is of 10,000 pages. Okay, 10,000 pages, and you have around 50,000 requirements, 60,000 requirements. So the idea is there are no labels, and the idea is how you can cluster similar requirements with the similar topic. So here you see. Train and signaling control system, train control and signaling system shall control the movement of following trains to avoid frequent occurrences of train breaking. So this is the requirement about operation of trains in mobility domain. And what we do is like we do topic modeling in a sense that we could do information retrieval. How can we cluster all similar requirements with a similar topic like operation of trains? Or how can we retrieve similar requirements having the similar topic like operation of trains? So here you see the proposal. This is the selected requirement in the tender, and you see the retrieval, the first retrieval, with a confidence of 87%. Similarly, you saw the third proposal, and you see that we also learn SNTCS, the acronym, the relationship between acronym and the expansion, with a score of 94%. So this is an application of topic modeling that what we have implemented in product. And the next one is building knowledge graph. So you have a turbine, and what we do is like we generate a timeline of turbine. So we have turbines. Siemens has a lot of turbines. So we get PDFs, XML, service reports, and we put it on our NLP pipeline, and we ask the system to generate a timeline of parts. First, let's say you have a part like flame detector. So when was the flame detector installed? When was it inspected? When something was replaced? And what was the cause of replacement? So it is all about entity extraction, relation extraction, and nothing more than that. So the idea is you do a replacement type of relation extraction, and then you do some kind of one array relation extraction to identify the cause of relation. I just wanted to give an example, but maybe I skip over. I show this example like damage mode also. The row 3 and row 4 veins show erosion. This is such kind of problems, or let's say such kind of service reports we receive. So the idea is to extract those kind of damage modes. We say that row 4 and row 3 and row 4 have damage mode, and the damage mode is erosion. We also build knowledge graph, like we crawl the public corpus, and we learn relationship, like company-company relationship, which is acquisition, for example. We also extract relationship between company called customer of, in order to have a knowledge base of customer suppliers that can be used for market intelligence. And this is how the knowledge graph looks like. You have a company, and then you have the list of properties, and we do entity and relation extraction to populate in the information for extraction or triples in knowledge graph. Thanks. Any questions?
Hi. I have a question. In all your model, I see you use a lot of vectors and vectorizing representation of the knowledge, and that then the use of the real application in a sort of a tree or a ontology is more manual or given.
Mm-hmm.
Is there any way you would integrate this kind of tree knowledge representation, or are you using this knowledge representation in a three-way, so on a hierarchical level in your system, or is it only given as a box to fill, but your tool?
Yeah, so good question. In industry, we have some kind of a catalog. So you have a product, okay, that's what you refer to. It's called catalog, and in catalog you see, let's say you have a part, and then you have subpart, subpart that consist. So we use that information, actually the catalogs, in order to annotate our entities. And we learn this relationship. We have a free text also. We use catalogs, we use free text in order to learn representation, which has this tree structure, hierarchical information encoded.
But not the other way around.
Not the other way around, yeah. It's a combination.
We have time for one more question.
Oh, yeah.
Yeah.
Yeah, so you were just a bit fast on the entity relationship extraction, and I didn't quite understand. So it's a supervised data set, I assume, and are all the entities that you try to classify then in different sentences? Can you just go into a little bit more detail about that part?
Yeah. So I talked about relation extraction only across sentence boundary. So we do entities within sentence, and then we extracted relationship across sentence boundary. So what we do is, like, we take all the pairs of entities at a particular distance, let's say distance of 5 sentence number. So we look at 2 entities, and they could be at a distance of 5, and then take all such entities as candidates and perform relation extraction. So this is the only step that we have across sentence boundary to extract relationships, if I answered you correctly.
Okay, so it's just there is a relationship, it's not what type of relationship it is?
Yeah, we have the label for it. I mean, this could be any type of relation. If it is not, then it is other type, means none or unknown, I would say.
And the data set you showed was always relationship extraction over multiple sentences, or it was just a subset of that task?
Sorry, I didn't get it.
Just the benchmark, the
Yeah.
data set that you showed.
Yeah.
I didn't quite get the name, but I'm sure I'll find it in the notes. So are they always in multiple sentences?
Yes, they are within also and across also. They could the relationship could be within the sentence also, and they could be across the sentence also. Yeah. This is called bio-NLP dataset. You can check out that. Bio-NLP. It's from medical domain. The paper is also available. We also released the data. You can check out the data.
So thanks again, Pankaj.